Hi, this is SN and welcome to my channel Concept of Mechanical Engineering. We have already completed the first chapter, which was Basics of Thermodynamics, and now we are going to start our new chapter, which is the second chapter of Thermodynamics, that is energy interaction. Heat and work. Here in heat and work, we will study heat transfer and work transfer. Let us start with work transfer. So what is work? Work is said to be done if the sole effect external to the system can be equated to raising of a weight. Weight may not be lifted. So work is said to be done by the system if the sole effect on things external to the system can be equated to raising of a weight. Note, weight may not actually be raised, but the sole effect will be equated to the raising of the weight. So this is the definition of a work transfer. Now we will see this with an example. Let us consider one motor. This is our motor and this is its shaft, and this motor is powered by a battery. This is the terminals of a battery and this is our battery. Let us hang one weight to the shaft of this motor, and now consider this as our system. So consider this as a system. Now if we'll make somebody to sit here, then what he will see? He will see that there is a transfer of electrical energy through the boundary of the system. So here electrical work is done. So here electrical work. Now the same example, if we change the boundary of the system, this is our initial example. This is battery and this is motor. This is the shaft of the motor and to its end weight is hanged. Now if we consider this as our system, so if we consider this as our system and make that somebody to sit here, then what he will see? Now this is the boundary of the system. Now it will see that rotation of the shaft. So here shaft work. Now in the same example, if we change the boundary of the system, this is motor, this is the shaft, and this is the weight. This is powered by a battery. Now if we make this as our system and put somebody here, then what he will see? He will see that lifting of weight. So here work is done, that is lifting of weight. Now in the same example, if we further change the boundary, now we will consider this whole as our boundary and put somebody here. What it will see? What he will see? He will see that there is no work. See, in the first example we have chosen this as a system, so here electrical work was done. We have extended the system and included the motor inside it. Then shaft work was this work was the shaft work, and further we have extended the system, then it was the work lifting of weight. And if we consider the whole as a system, then there will be no work. So what happens? The work is depending on the boundary. So we can say that work is a boundary phenomena. Here work means work transfer. We are dealing with work transfer. Note, work transfer depends on the boundary of the system and hence it is boundary phenomena. Boundary phenomenon. So work transfer is a boundary phenomenon. Now we will deal with some examples related to the work transfer. Some of the examples which also comes in the examinations, in different examinations, in competition examinations as well as in semester examinations. See, let us consider one beaker or container which is insulated, and inside it gas A is there, and this is our electrical heater. So what is transferred to gas? Gas A. Is there any heat transfer? No, there is no heat transfer. Work transfer? Yes, electrical energy is being crossing the boundary, so there is work transfer. And since the heat is not crossing the boundary, so there is no heat transfer. In the same example, we will change a little bit. Let us consider now this insulated system in which gas A is there, and inside it there is another beaker in which gas B is there. Now it is insulated. So again this is the electrical heater. Tell me now, what is transferred to gas? A and B. For A, is there any heat transfer? No. Since it is insulated, there is no heat transfer. Is there any work transfer? Yes, work is being crossing the boundary, So this is work transfer. For gas B, is there any heat transfer? Since it is insulated, so there is no heat transfer. And work transfer, since work is also not crossing this boundary, so there is no work transfer. In the same example, we will change a little bit. This is again our insulated system, and this is the heater, and this is gas A, and inside it there is gas B. Now it is not insulated. Now tell me what is transferred to gas A and gas B. Obviously for gas A, as we have already seen that there is no heat transfer, but there is work transfer. For gas B, now it is not insulated, so there is heat transfer, but that work is not being crossing its boundary, so there is no work transfer. Now we again alter a little bit in the given example, and we'll see what happens. Now this is our system. Again, this is insulated system. Inside it there is another system B, in which gas B is there, and this is gas A. Now we put the electrical heater outside that system. Now the question is, what is transferred to gas A and B? For gas A, is there any heat transfer? Since the system is insulated, so heat cannot cross its boundary, so there is no heat transfer. And for gas B, since the heat is not entering this system, so there will also be no heat transfer for gas B2. Now work transfer for gas A. Since that electrical energy is not entering its boundary, so there is no work transfer. The same thing is here also, so there is no work transfer. Now we will change a little bit in the given example and see what happens. We have the same system in which gas A is there, and there is another beaker in which gas B is there. Now both are not insulated, and we have kept the electric heater here. So question is, what is transferred to gas A and gas B? See, the system is not insulated, so we can easily see that the heat can transfer, heat can cross this boundary, so there is heat transfer. So there is, for gas A, there is heat transfer, and since this electrical energy is not crossing its boundary, so there is no work transfer. But for gas A, for gas B, heat can transfer because this is not insulated, so heat can enter in this system, and through that it can enter here also, so there is heat transfer. But there is no work transfer to the system, since the work is not entering here, the electrical energy is not crossing its boundary, so there is no work transfer. So we have seen that heat transfer depends on the boundary, so it's a boundary phenomenon, and we have also seen different questions related to its that work transfer and heat transfer. Now we will see sign convention of heat transfer, sorry, heat work transfer, because we are studying work transfer. So we will see that what is the sign convention what we use for work transfer. This is our system. The heading is sign convention. Sign convention of work done. See, if work is done on the system, so work is done on the system, then this is negative. And if work is done by the system, work is done by the system, then we consider it as positive. So if work is done on the system, then it is negative, and if work is done by the system, then it is positive. This is the sign convention of work done. Now we will see generalized equation for closed system or non-flow process work. So let's see generalized equation for closed system or non-flow process work. So this is our heading. Let us consider one piston cylinder system. This is our piston cylinder, and this is the initial stage of the piston. We will take this as axis. Now if we displace this piston further, that is, we will get this position of the piston. This is the final position of the piston. This is the axis. This distance, or this is called as displacement. So this is the displaced volume, dV. This is our system, and A is the cross section area. Now the differential work we can write here dW as force into displacement. We know that work is equal to force into displacement, so we can write dW as F into dx, and if we integrate this one, we will get the total work. We know that this force equals to, pressure equals to force by area. So this implies force equals to pressure into area. We can put here, we will get dW as integration of, in place of F we can put PA into dx. Now this area into dx, area into displacement, we know that area into displacement equals to volume, that is dV here. See, this is the cross section area and this is the displaced length, so this area into this length is the volume. So in place of this A into dx we can write dV. So integration of dW is equal to pressure into dV. Now total work equals to integration of P dV. This is our generalized equation. We have taken assumptions here, so we can write here assumptions for this formula First one, system should be closed system. Process must be reversal process. And the third one is work should cross the boundary. So for this formula we have these assumptions. So first assumption is system should be a closed system, process must be reversal process, and work should cross the boundary. Then only this formula is valid. Otherwise, if we will not have this assumption, then this formula is not valid.